Hi students, it's Dr. Neeraj Upadhyay to deal another lecture of the title Valence Bond Theory Approach for Understanding Chemistry of Coordination Compounds. In last class, you identified structural and stereoisomers of the coordination compounds. There you studied about the compounds having similar molecular formula but different structures. Physical, chemical and biological properties of the molecule do relate with the structure of the molecule, and therefore molecules with difference in structure but identical formula have their own existence in the chemical world. Compounds having significant difference in structures mostly have different physical and chemical properties and frame structural isomers. They are mostly, we learned about cis, trans, facial, meridional isomers, etc. Compounds having similar molecular and structural formula but different orientation in three-dimensional space are called stereoisomers. There you divided stereoisomers into diastereomers and enantiomers. Such compounds rotate plane polarized light in different direction and therefore called optical isomers. Optical isomers have different optical properties and differ in rate of interaction with optically active compounds. A structure of a compound is the result of interaction of atoms with their atomic orbitals. So, understanding chemical bonding of any compound help in evaluating physical and chemical properties of the compound, and coordination compounds are not the exception of this. So, today we will learn about valence bond theory approach for understanding bonding in coordination compounds. The learning objective of this class is to grasp the concept of valence bond theory for understanding the bonding concept of coordination compounds and to become able to apply this concept. In order to understand bonding of coordination compounds, various theories were proposed. Valence bond theory, crystal field theory and molecular orbital theory are the most popular among them. Although crystal field theory and molecular orbital theory are considered more useful in understanding various applications of coordination compound, it is desirable to understand valence bond theory because the next two theories used the base model of valence bond theory. Before reaching to valence bond theory, let's revise some prior concept that you already know. You know, ligand contain a pair of electrons. For example, ammonia contain one pair, water contain two pairs, hydroxyl ion contain three pairs, and chloroligand contains four pair of electrons. These pair of electrons are occupied inside an orbital if this pair is donated by the ligand to the central metal for forming sigma bond. We call such orbital of ligand as sigma orbitals. Similarly, transition metal offers vacant orbitals for formation of bonds with ligands. These vacant orbitals are able to accommodate the pair of electrons provided by ligand. The bond formed between the two are called coordinate bond. The number of such bonds depend on number of vacant orbitals of suitable energy provided by the central metal. These orbitals of suitable energy combine to produce new set of orbitals having equal energy and called hybrid orbitals. As you know, s orbital is spherically symmetrical, p orbitals are dumbbell shaped, orienting towards the different Cartesian coordinates x, y and z axis, and therefore these three orbitals are called px, py and pz orbitals. Similarly, d orbitals are of double dumbbell shape, can be oriented either in the x, y and z axis called dx square minus y square and dz square, or can be oriented in between the axis called dxy, dyz, dzx orbitals. It is therefore d orbitals can be considered in two different shapes: orbitals orienting towards the axis or orbital orienting in between the axis. Set of two d orbitals orient towards the axis and called dx square minus y square and dz square, while set of 3 d orbitals that are dxy, dyz and dzx orient in between the axis. Some of the vacant orbitals of central metal atom or ion may combine and hybridize to produce equal number of identical energy orbitals. These orbitals are called hybridized orbitals. For example, combination of one vacant s and 3 vacant p orbitals on hybridization produce 4 sp3 hybridized orbitals, while combination of n-1 dx square minus y square, ns, npx and npy produce dsp2 hybridized orbitals. Certainly, overall energy of 4 dsp2 hybridized orbitals is lower than the energy of sp3 hybridized orbital for the same metal, as dsp2 contain d orbital of lower energy shell or penultimate shell. Similarly, combination of 1 ns, 3 np and 2 nd orbitals of the same energy shell on hybridization produce 6 hybridized sp3d2 hybridized orbitals. Energy and shape of all the 6 hybridized orbitals are equivalent. sp3d2 hybridized orbital produces octahedral geometry. An octahedral geometry can also be produced if 2n-1 d orbitals, 1 ns orbital, 3 np orbitals produces 6 d2 sp3 hybridized orbitals. Here, 2 involved d orbitals are from n-1 energy level, that is from the penultimate shell. Obviously, energy of 6 hybridized d2 sp3 hybridized orbitals are lower than of 6 sp3d2 hybridized orbitals. Here in the table, coordination number, hybridization and molecular geometry is summarized. sp hybridized orbitals produce coordination number 2 and has linear geometry. sp2 hybridization produces coordination number 3 and trigonal planar geometry. sp3 hybridization produce coordination number 4 and a tetrahedral geometry, as they involve the orbitals having orientation in x, y and z axis. dsp2 hybridized orbitals, where d is dx square minus y square orbitals and 2 involved p orbitals are px and py orbitals, also provide coordination number 4 but produces two-dimensional geometry oriented in x and y direction only and raise square planar geometry. Similarly, 5 hybridized vacant metal orbitals may involve n-1 dz square orbital to produce 5 hybridized dsp3 orbitals that produces trigonal bipyramidal geometry. Coordination number 5 may also be produced by formation of sp3d hybridized orbitals, where participated d orbital is of valence shell and dx square minus y square in its orientation. The geometry produced by such hybridized orbitals is square pyramidal. The hybridization and shape produced by coordination number 6 we have already dealt. Now, let's begin with the postulates of valence bond theory. The first postulate is, in a complex, central metal atom or ion provides a number of vacant d orbitals of suitable energy for the formation of bond with the ligand. The total number of such vacant orbitals provide coordination number of the central metal atom or ion. The second postulate says the vacant metal orbitals hybridize to produce equal number of new orbitals of equivalent energy called hybrid orbitals. The shape of hybrid orbitals decides about the geometry of the complex. For example, if central metal produces 6 d2 sp3 hybridized orbitals, the shape of molecule will be octahedral. The third postulate is, each ligand must at least have a sigma orbital containing a lone pair of electrons. The fourth postulate is the filled sigma orbitals of the ligand overlap with the vacant hybrid orbitals of the metal to produce ligand metal dative or coordinate bond. The number of such bonds depend on number of vacant orbitals produced by central metal. The d orbitals involved in hybridization may be inner d orbital or outer d orbital, that is either n-1d or nd. The produced complexes by these two ways are called low spin and high spin complexes respectively. The formation of low spin and high spin complexes can be predicted by comparing value of experimental magnetic moment of the complex with the theoretical spin only magnetic moment value obtained by the formula mu effective is equal to root under n into n plus 2 Bohr magneton, where n is the number of unpaired electrons. Intentionally, we have represented number of unpaired electrons with capital N here to avoid the confusion between the number of unpaired electrons and principal quantum number. Bm is the unit of magnetic moment, the full form of which is Bohr magneton, and can be determined by the formula 1 Bm is equal to Eh by 4 pi mc, where E is charge of an electron, H is Planck's constant, m is mass of electron, and c is velocity of light. Now, let us elaborate the valence bond theory by taking some examples. Our first example is NiNH3 whole 4 2 plus, means tetraamine nickel second complex. This complex is a diamagnetic complex having mu effective value 0. Can you predict hybridization geometry and type of complex is this? Means I want to say, can you predict this compound is a low spin or high spin complex? The central metal ion of the complex NiNH3 whole 4 2 plus is Ni2 plus. The electronic configuration of nickel here is 1s2, 2s2, 2p6, 3s2, 3p6, 3d8, 4s2, while the electronic configuration of Ni2 plus is 1s2, 2s2, 2p6, 3s2, 3p6, 3d8 in its ground state. The orbital picture of the same would be ammonia is the ligand, each of which provides a sigma orbital containing a pair of electrons. Since there are 4 ligands combining with Ni2 plus, therefore the coordination number of nickel here is 4. It means Ni2 plus provides 4 hybridized vacant orbitals. The coordination number 4 can be achieved by 2 different types of hybridization, that is sp3 or dsp2. For sp3 hybridization, 1 4s and 3 4p orbitals should hybridize to produce 4 sp3 hybridized orbitals that can result a tetrahedral geometry for the complex. In this case, total number of unpaired electrons is equal to 2 and theoretical mu effective value is equal to root under n into n plus 2, that is root under 2 into 2 plus 2 equal to root under 8. The value will become 2.83 Bohr magneton. But actual value or experimental value of the complex doesn't match with this. The other possibility of hybridization for coordination number 4 is dsp2, where 8 3d electrons are forced to be occupied in 4 3d orbitals only, making 1 d orbital, that is dx square minus y square, vacant. The 4 dsp2 orbitals then may combine with 4 sigma orbitals of ammonia. By this way, as we can see, there is no unpaired electron available and therefore theoretical magnetic moment will become 0. So, mu effective is equal to root under n into n plus 2, where n is equal to 0. So overall value of mu effective will become 0. This value of magnetic moment matches with the experimental value of NiNH3 whole 4 2 plus. Therefore, the given complex is a low spin complex formed by dsp2 hybridization of Ni2 plus for producing square planar geometry of the complex. Using similar method, can you predict hybridization and geometry of CuCl4 3- ion? Here Cu plus has D10 configuration, making none of the d orbitals available of hybridization, leaving only one possibility of hybridization for coordinate number 4, that is sp3. This complex is diamagnetic. Let's move towards understanding valence bond approach for coordination number 6. The possible hybridization for coordination number 6 is D2sp3 or sp3d2, producing low spin or high spin complex. Let's begin our study by taking some examples. FeH2O whole 6 3 plus is a paramagnetic compound having magnetic moment near 6 Bohr magneton. Determine whether the complex is low spin or high spin. So let's solve this question. The central metal ion of the complex FeH2O whole 6 3 plus is Fe3 plus. The electronic configuration of iron is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. While the electronic configuration of iron plus 3 oxidation state is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5 in its ground state. The valence orbital picture of the same would be the coordinate number is 6 that can be achieved by two different ways, that is either by D2sp3 hybridization where involved d orbitals are two 3d orbitals, or by sp3d2 hybridization which is resulted by involvement of two 4d orbitals, that is 4dx square minus y square and 4dz square orbitals. Now let us start with possibility 1. For producing 6 D2sp3 hybridized orbital, all the 5 d electrons have to be occupied in 3 orbitals only, producing low spin complex having only one unpaired electron. By this way, theoretical value of magnetic moment would be mu effective is equal to root under n into n plus 2 Bohr magneton equal to root under 1 into 1 plus 2, that is 1.73 Bohr magneton. This value doesn't match with our experimental value of magnetic moment. The next option is sp3d2 hybridization by central metal ion orbitals. In this case, there is no need of rearrangement of 5d electrons, as participated orbitals in such type of hybridization are 1 4s, 3 4p and 2 4d orbitals. Therefore, total number of unpaired electrons available after formation of such complex is 5. Therefore, mu effective is equal to root under n into n plus 2 Bohr magneton, that is root under 5 into 5 plus 2 Bohr magneton equal to 5.92 Bohr magneton. This value is very near to the experimental value, and therefore with 5 unpaired electrons, FeH2 whole 6 3 plus is producing a high spin complex with sp3d2 hybridization. Similarly, you can apply the concept to different coordination compounds. Try to solve the questions given in the exercises, but here I want your special attention towards a genuine confusion where valence bond theory is not very convincing. Let's discuss a case of CuNH3 whole 4 2 plus. The experimental value of magnetic moment is around 1.8 Bohr magneton. So, can you draw the conclusion about the hybridization and structure of the molecule by learning this? Let's start applying the valence bond concept in this case. Here, central metal ion is Cu2 plus. electronic configuration of Cu is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. While electronic configuration of copper in oxidized state is 1s2, 2s2, 2p6, 3s2, 3p6, 3d9. The valence orbital picture will be therefore, since 4 ammonia ligands surround the central metal ion, the coordination number of Cu2 plus is 4. The coordination number 4 can hybridize 4 vacant central metal ion orbitals in 2 different ways. Either 1s or 3p orbitals may hybridize to frame 4 sp3 hybridized orbitals and may generate tetrahedral structure. Or 1d, 1s and 2p orbitals may hybridize to form 4 dsp2 orbitals that frame a square planar geometry. Here I have a question for you. Can you determine the value of magnetic moment for the individual possibility of the formation of sp3 or dsp2 hybridization of the central metal ion in the complex CuNH3 2 plus. In any of the cases, total number of unpaired electrons will remain 1 and value of magnetic moment would be mu effective is equal to root under n into n plus 2, that is root under 1 into 1 plus 2 equal to 1.73 Bohr magneton. In our first look to the 5d orbital picture of the copper ion, it seems impossible to occupy 9th electron in the 4d orbital, and therefore dsp2 hybridization or a square planar geometry seems impossible. Only we predict formation of sp3 hybridized orbitals with tetrahedral structures. Unfortunately, with X-ray diffraction analysis, the structure of CuNH3 2 plus was found to be square planar. To explain the case, it was suggested that due to repulsion placed by 4 ammonia ligands, the 9th electron of d orbital of Cu2 plus ion may jump to 3rd 4p orbitals, making a d, 1s and 2p orbitals available for hybridization to produce dsp2 orbitals, and a square geometry will result. Now let's move towards the limitations of valence bond theory. Though the valence bond theory is easy to grasp and is able to frame a preliminary structure of the complex compound, but has certain number of limitations too. Here are these limitations. Valence bond theory is full of assumption and lack with solid proof behind such assumptions. The second limitation is the low spin and high spin complexes is predicted by the application of magnetic moment, but by the time you cannot predict magnetic moment of the compound using this theory. The theory does not answer why metal and a number of ligands combine to form a complex compound, because here in this theory we find several violations of effective atomic number rule. The theory cannot be applied to determine the color of the complex, which is one of the major observation in the coordination compounds. The fifth limitation is there is no quantitative estimation in this theory. The term stability, which is comparative in this primary concept, cannot be therefore determined using this theory. The verdict can be extended to the form that the theory is unable to predict about thermal and kinetic stability of the complexes. In many cases, it gives a state of confusion in terms of structure of molecule. The theory is dependent on the value of magnetic moment. If magnetic moment fails to conclude anything, then the prediction of the structure becomes difficult by this theory. For example, the theory doesn't explain the geometry of CuNH3 2 plus convincingly. In this theory, ligand was not been separated in accordance with their strength. valence bond theory assumes participation of valence bond orbital for the formation of coordination compound. Central metal were assumed to provide vacant orbitals equal in number that are required for the formation of bond with the ligands. These vacant orbitals hybridize to form equal number of equal energy orbitals. Ligands provide sigma orbitals containing a pair of electrons that overlap with the hybridized vacant orbitals to form equal number of coordinate covalent bond. The structure of the molecule is dependent of the type of hybridization, which depends on the formation of low spin or high spin complex. The possibility of low spin and high spin complex were verified by using magnetic moment tool. Though the theory was easy to understand but seems less useful as is focused on the bonding on coordination compound only, and properties associated with such compounds like magnetic properties, color, extra stability, etc. of the complexes cannot be predicted by this theory. Also, the formation of low spin and high spin complexes is predicted by the value of magnetic moment. But if magnetic moment fails to give any clue, it is almost impossible to predict whether the framed complex is low spin or high spin. So, this was all about the valence bond theory approach for the formation of coordination compound. In the next lecture, we will deal about crystal field theory for understanding bonding and application of coordination compounds. Thank you very much for listening me. Please solve the question of this module. Thank you again.